Good morning, ladies and gentlemen. We've previously spoken about capacitors in the electrostatics unit, but now we're going to talk about capacitors in RC circuits or resistor capacitor combination circuits. Okay, so basically an RC circuit is just a capacitor is used with a resistor within a circuit. Okay, it's just simply a combination of R and C together. But the most important thing to remember about RC circuits is that capacitors want to charge. Meaning, when this switch over here is first flipped, okay, current flows as it normally does in the beginning. Meaning that as the charge comes out, even though there's a break between the plates, okay, as the plate is filling up, it's through induction, it's pushing charges to return into the battery. So the battery believes that there's a normal current flow, even though technically there's a break in between the capacitor plates. And notice that as the plate is charging, okay, initially there's no potential difference over the plate, but as it's connected to the battery for a long time, the voltage of the capacitor becomes the voltage of the battery itself. Now the thing is, okay, over here we can see a battery connected with a capacitor, and when the battery is first turned on, notice what's happening to that current over here. It's decreasing and decreasing and decreasing as the capacitor is increasing in charge. Meaning that as the plates fill up with charge, the battery is finding it more difficult to continue pushing charge on. So therefore, after a long time, keyword being a long time, normally you can use calculus to calculate this, but basically a fully charged capacitor does not allow for any current to flow through anymore. Meaning instead of having an I going through the capacitor, now we have a Q, a positive Q and a negative Q, of course, on each plate. But that means that there's no more current, meaning that this resistor ultimately gets turned off. Because there's no current passing through. However, look what happens. Initially, when the capacitor is placed in here, we have a parallel circuit in a series circuit. Okay, the 1 and the 1 over there are both parallel to each other. But after it's charged for a long time, that means no more current can flow through the 1 ohm resistor. So now it's therefore only a series circuit. Okay, so always keep in mind, whenever a capacitor is fully charged, it completely blocks off the current. So in this case over here, as similar to a diagram before, if the capacitor became fully charged, the resistor would just turn off. There would be nothing left on at all. Over here, this is a more interesting example. The capacitor is placed in parallel with resistor 2. So because it's placed in parallel with resistor 2, that means that the voltage of this capacitor, because it's in parallel, would equal to the voltage of resistor 2. Okay, it would not equal to the voltage of the battery itself. It would only equal to the voltage of resistor 2. Initially, when the circuit is turned on, the capacitor starts to charge, and R2, so initially, R2 is dim because it has to share current with the capacitor. But after a long time, there's no more current passing through the capacitor, so R2 is brighter. Okay. In this example over here, it's very similar to the one before, except that now the capacitor branch is also connected to R2. So after a long time, R2 would initially be on, R1 would be dimmer because it's sharing current with R2, but after a long time, R2 would simply turn off, and this would become a series circuit also. So right now, I've taken the problem and I've put it into the whiteboard, and let's create some numbers. I attached a 12-volt battery to it. I included a 5 ohm, 10 ohm, and 15 ohm resistor attached to a 20 microfarad capacitor. And the key point here will be that the capacitor has been charged for a long time. And ultimately, I want to know how much charge is on the capacitor. The incorrect method of solving for this problem would be to automatically take the battery and the capacitance and do Q equals to CV. Because even though the 12-volt battery is attached to the circuit, the capacitor is not getting all 12 volts. So we actually have to solve for the voltage that's passing through the 10 ohm resistor, because the capacitor is connected in parallel to the 10 ohm resistor. So we first solve this as if it was just a simple series circuit. And we'll just pretend as if that capacitor isn't even there. So if I'm solving for it as a simple series circuit here, and if I do an RVIT chart, I know I have a 5 ohm resistor, a 10 ohm resistor, connected to a 12-volt battery. Because this is a series circuit, I know that in a series circuit, the resistances simply add up. So my total resistance would equal to 15 ohms. And of course, knowing that I is equal to V divided by R, I can solve for I to equal to 0.8 amps. In a series circuit, of course, also, we know that I is the same throughout, which means that 0.8 amps is at every location. So therefore, if I then do V equals to I times R, 0.8 times 5, 0.8 times 10, I end up with 4 volts and 8 volts. The one I'm interested in, of course, is the 8 volts, which is 10 ohm resistor. So that means that this capacitor over here, as the 10 ohm resistor gets 8 volts, that means that the capacitor also gets 8 volts passing through it. So now, if I do Q equals C times V, this is simply equal to 20 microfarads times 8 volts, which ultimately will equal to 160 microcoulombs.